I'm going to show you how to do implicit differentiation today, which means we're going to find the derivative of implicitly defined functions. I'll show you what implicitly defined functions are. But really all we're doing is implicit differentiation. We're doing the exact same thing as the normal way using the chain rule. If you haven't watched my chain rule video, I suggest you pause, go find that and watch it before you come back. So we're getting to the idea of implicit differentiation. What would f look like if we recomposed instead of sine of y? It would look like sine of x squared. By now, you should be good at using the chain rule. We use the chain rule when a function like x squared is the input to another function like sine. And so you should be pretty good at saying the derivative of sine of something is cosine of something, or something is an x squared, which has a derivative of 2x. Okay? You'll see what we do on the next page is basically the same thing. What I need to point out is, what is that 2x? Well, y is equal to x squared, which means if we went back up here and took the derivative of y equals x squared, we'd write dy dx is 2x. So really, if we were doing this like we normally do the chain rule, we would have written cosine of y times dy dx. The implicit stuff you'll see in a moment is your answer kind of looks like this last thing. We don't solve for y, or we don't want to solve for y. So we pretend like, well, if I did solve for y, I'd write it here, and I'd chain rule write the derivative or multiply by the derivative of that function later. This is basically the same problem, but I've hidden the function we're going to put inside of cosine. So using implicit differentiation is like, well, y is some other function. It doesn't matter what that function is, so we just pretend like we know what it is. And what's the derivative of cosine of something? It's negative sine, in this case, of y. But notice, we wrote f prime of x, which means the input variable to cosine is eventually x. Like there's some version of x hiding underneath here. And so, since this y must be another function, we treat it like we would x squared. If y was x squared, we'd write negative sine of x squared times 2x. And if y was tangent, we would have written negative sine of tangent multiplied by secant squared of x. However, we don't know what y is, so we do this implicitly by just saying, well, I don't know what y is, but I know y is a function, so I better multiply by the derivative of y. You could have also written y prime. It doesn't really matter in terms of notation. A lot of people are bothered by not seeing what's behind that box, so let's fill that in. And so now, since we know what's in there, we would write negative sine. What would you put now that you know what y is? You'd put a square root of x here. And what do you multiply by? You multiply by the derivative of the square root of x. 1 over 2 times the square root of x. Hopefully you're thinking, well, if I had to find that derivative, I'd just do it the chain rule way. I agree. We're going to get to derivatives that you must use, or it's better to use implicit differentiation for very soon. Let's try that again, though. So y is some function, and we don't know what it is. That's okay. We can still write what we would do, and that's the implicit part. We're not doing something, we're sort of leaving instructions. So the derivative of sine of y is cosine of y. But remember, y is some other function that has an input of x. And so the chain rule applies, and we have to multiply by the derivative of y. What's underneath that gray box? Oh, it's the square root of x again. Knowing that, what would we have done? Well, we left instructions to ourselves. If you knew what y is, that y would be inside of cosine. So square root of x goes inside of cosine. And if you knew what y is, you'd multiply at the end by the derivative of y. And we can do that now. Okay, so imagine you just have y cubed. But the important part is this says the derivative with respect to x. Okay? That means this y is some function y equals, I don't know what, maybe sine of x, maybe cosine of x, maybe x cubed. Who cares? We just pretend like we know. The derivative of y cubed with respect to x is 3y squared, because y is some function, times the derivative of y. Okay. In case you're wondering, what's this respect to x stuff? Maybe we should explain that. So I'm going to erase what I have here. And let's just cover up our x and say with respect to y. And let's just pretend that's not an x. So let's say we have f of y is equal to y cubed. What's the derivative of y cubed with respect to y? Just 3y squared. Because this respect to y stuff means y is an input variable. Okay. Back to normal. Okay. So let's do this derivative implicitly on the left-hand side, and then we'll compose on the right-hand side, and hopefully everything matches. So the derivative with respect to x of y cubed is 3 times something squared. Remember, y is some function, so we'd have to multiply by the derivative of y at the end. Okay, that's the implicit stuff, but we were told later y is x cubed, so we'll write 3 instead of y, x cubed squared, and I'm hoping you can do dy dx, the derivative of x cubed, in your head, 3x squared. Normally, we shouldn't simplify, but we're trying to find out some information here. Let's see what we have. 3 times 3 is 9. X cubed squared is x to the 6th power, times 2 more x's is x to the power 8. All right, let's rewrite f of x instead of y cubed. We'll replace y with x cubed. So f of x is 3 versions of x cubed. That's x to the power 9. And that's a very easy power rule. 9x to the 8th power. Hey, at least they match. So this is finally a good example of when you should use implicit differentiation. Could you solve this for y? Like 5 minus x squared and then take the square root? You could. Can you imagine that? Good. That's what this y is. This thing that you would solve for, that's what's being squared. So think of this as, well, your normal x squared plus some function squared is equal to 5. Okay. Hopefully you know x squared plus y squared equals 5 is a circle centered at the origin with a radius of the square root of 5. So this intersection point right here would be root 5, 0. Okay, so let's take the derivative of x squared with respect to x. That means x is the input variable. Easy, 2x. What's the derivative of some function squared? It's 2 times that function to the 1st power. That function is y, which has a derivative dy dx. Ooh, not 5. The derivative of a constant is 0. So this piece in the middle is the weird part. What's going on there? Remember, we're treating y like some other function, just like we would be doing the chain rule. Okay, so what if you had sine of x squared? How do you do that derivative? You do 2 times sine times cosine. That's what we did here, except we didn't want to solve for y, so we just write, if I knew what y was, it would be 2 times that y, and then I'd multiply by the derivative of y using the chain. However, we're not quite done. Even though we did derivative work, the derivative should be like dy dx equals. So we do some algebra, and hopefully you can do this in your head. We are going to subtract 2x and divide by 2y. dy dx is equal to negative x over y. Let's see if this makes any sense using the one-ordered pair I wrote, square root of 5, 0. So let's see, using root 5, 0. Some of you already know what we're going to get. Oh no, we're going to get an eraser. Well, let's just pretend that's the tangent line we're looking for. Okay, well, x squared plus y squared equals 5 doesn't have a derivative at root 5, 0 because a vertical tangent doesn't count as having slope. So dy dx is equal to negative square root of 5 over 0. And remember, dy dx is a slope, so, well, this slope is undefined. Let's find a more useful point. How about 1, negative 2? That should give us a slightly positive derivative. So let's see, using 1, negative 2, let's see, dy dx is equal to negative 1 over negative 2, so that's 1/2. Well, the sign is at least correct, and that seems like a reasonable slope. So this is a great time to use implicit differentiation. We don't really want to solve for y, and we got a pretty useful derivative. If we had solved for y, we would have had y as plus or minus the square root of 5 minus x squared, which means doing the derivative, well, this is really two functions, the top half of the circle and the bottom half of the circle, and then we'd need two derivatives, and we'd have to choose the right one.